Hello, everyone. Uh, Welcome to the INQA seminar series. Today we have a talk from Samyak Jhaveri from UC Irvine.
Hi, thank you for the introduction. I'd like to talk about quantum computing and its use for software engineering purposes. And my specific topic is right now is code clone detection, which is essentially finding a way to formulate the code clone detection problem as an optimization problem and then solving it using quantum annealing. Um, so I'd like to go over the parts of the presentation with starting with the introduction and a little bit of information about what is the code clone detection problem, and then moving on towards how I formulated the software code clone detection problem as an optimization problem, and then talking about the experiment design and the results and analysis that we did using quantum annealers and the future work and the future directions that this can take. But why code clone detection? It's an extremely important area of software engineering because code clones and the presence of code clones in large software systems can affect the maintainability, the quality, and the repairability of these large software systems. And um, code clone detection, code clone detecting tools have applications from plagiarism detectors in academic situations to large-scale code systems to improve their uh, code execution. So essentially code search and code optimization. But what is code clone detection? Um, for example, if you have two pieces of code, the first one here being the original one, it's a simple piece of code. And the second one here is a code clone of itself, which is um, there is some modifications done to this original piece of code to in this new piece of code. As you can see, the num is expressed differently. So, and abstract syntax trees are an intermediate representation of code in such a way that the semantic information of this code is retained in the form of a tree data structure. And that is essential for helping the compiler understand what is actually happening in the code. So there are two main types of code clones. The first is syntactic code clones, which means that they're textually similar and functionally similar with some modifications here and there. And then there are semantic code clones. So semantic code clones have the same essential functionality, but they're written differently. Um, the syntactic code clones are categorized into three categories, which is type 1, type 2, and type 3, where type 1 are just code clones that have their comments or white spaces modified. And that's the only changes that are made to them. Type 2 code clones or renamed code clones essentially have their variables or other identifiers renamed from the original code fragment. And type 3 clones, which are also called near miss clones, essentially are type 2 clones with some names changed. But what's different about type 3 clones is that um, in it, you can have some lines added or removed. So if you see the example here, this one has 4 lines of code, and this one has 2 because the way that the num variable is defined is different. So that makes the second one a type 3 clone. Now, type 3 clones are very difficult. And then lastly, we have type 4 clones, which are essentially the same, but have uh, but have been written differently, like expressing a for loop as a recursion, which has the same functionality but different approach of writing. Um, I need not go over these terms. You already probably know them. Okay, so what's the motivation behind this work? Code clone detection is an important software engineering problem. We know that, and it is an actively studied area of research in software engineering. Type 3 code clones, the ones that I just mentioned with the ordering changed or with some lines added or removed, are very difficult to detect, and they're computationally intensive to detect. There have been approaches that use uh, the graph representations of code in the form of abstract syntax trees, ASTs, or program dependency graphs, PDGs, and compare them. And from this comparison, they generate a similarity matrix to see how similar two pieces of code are. And depending on that, they're categorized into type 1, type 2, or type 3 clones. However, these are not always the best solutions. It requires aggressive heuristics to have good enough solutions for these approaches. Even though they have good precision recall, there are possibilities of false positives and false negatives. Um, one way is one way is to forego graphs altogether and express the code-clone detection problem as an optimization problem. So what I have done here is express the software code clone detection problem, a well-known problem in software engineering, and expressed it as an optimization problem so that it can be solved using a quantum annealer. And because we all know that quantum annealers are good at optimization, it is an interesting area of research of how such a problem can be expressed onto to be solved onto quantum annealers. So the contributions of my research are how to formulate the subgraph isomorphism problem uh, as amenable onto quantum processing QPUs. Although this is not the first implementation of the subgraph isomorphism problem on a QPU, it is the first implementation of the subgraph of the code clone detection problem expressed as the subgraph isomorphism problem to be solved on a QPU, as far as we know. I also introduced a method to incorporate additional node type based constraints into the formulation. And this constraint is essential for making it feasible to detect code clones using this technique. And finally, I also empirically validate the scalability of using quantum annealing for code clone detection for small code fragments. So talking about graph and subgraph isomorphism, um, so essentially graph isomorphism is comparing two given graphs and seeing if they're isomorphic or no by finding the mapping of the nodes and edges of one graph onto the other. And so essentially the function that represents the mapping is edge preserving and bijective. On the other hand, uh, we know that when comparing two pieces of code, it is possible that their abstract syntax trees that need to be compared may not be of the same size. So it means that instead of using graph isomorphism, we must use subgraph isomorphism to see if the smaller abstract syntax tree graph can be mapped onto the larger abstract syntax tree graph. And then their similarity measure is generated so that we know how similar they are or if there is a perfect mapping or no. So that's why we used subgraph isomorphism, where you try to map a smaller graph onto the bigger graph, and the mapping is essentially a function that is edge preserving and injective, which means that um, the smaller graph, all the nodes of the smaller graph must be mapped to any node of the bigger graph, but all the nodes of the bigger graph may or may not be mapped to a node in the smaller graph. So coming to the formulation of code clone detection as an optimization problem, the objective is to map the ASTs of one graph onto the ASTs of the other graph while minimizing the energy of that mapping. So the challenge in that is to specify the penalties in such a way that all the incorrect mappings are penalized, and that increases the energy of the QDO model so that it converges to the desired optimal solution. So essentially, we are solving the subgraph isomorphism problem by formulating a QDO to compare and map the one AST graph onto the other. We used two penalties for this for the initial formulation. The one with the node mapping penalty. So here you can see a given code and its clone and the ASTs of that given piece of code. And you can see here that whenever two nodes of G2 are mapped to the same node of G1, it violates the rules of injectivity. So essentially, the node mapping penalty penalizes any mapping from G2 to G1 that violates the rules of injectivity. Similarly, for the edges, every time there is an incorrect mapping from G2 to G1, it is penalized. So essentially, if there is an edge between two nodes in G2 and G1 being mapped to the corresponding nodes in G1, it has to check whether there is an edge or no. If the edge exists, then no problem, no penalty, you can map it. But if the edge in G1 does not exist, then it's penalized. So essentially, we're sieving out all the incorrect mappings just to keep the correct ones. And this should lead us to a good enough solution where if there is a mapping from G2 to G1, which is the smaller graph AST to the larger graph AST, we can find how similar the two given ASTs are, and therefore how similar the two given pieces of programs are. Coming to the algorithm, I'll just go over the algorithm once and then go into the detail of the individual components. Starting with defining G2 nodes as discrete variables and G1 nodes as their cases. So because we're using a DQM, a discrete quadratic model from the DWave Ocean suite, we are defining the nodes of G2 as the discrete variables that can be mapped to any of the nodes of G1, which can be the cases, the possible cases that they can be mapped to. And then we're penalizing the incorrect node-to-node mappings, and then penalizing the incorrect edge-to-edge mappings. And finally, we're penalizing the different node types. So in this penalty, what we're doing is after we penalize the incorrect node-to-node mappings and penalize the incorrect edge-to-edge mappings, we realized that in any given AST, when comparing two ASTs, it is possible that they may be of different types, the nodes. So if I can show you the previous slide, so as you can see here, it is possible for nodes of different types to be mapped onto each other, which would be a perfect topological mapping. But even then, that would be incorrect for code clone detection, because even if you manage to map a given node onto another node, but they are of different types, it means that in the code that there are different pieces of code, and they should not be mapped perfectly. So essentially, what the node mapping penalty does is that it compares the node types before mapping them onto each other. If the node types are the same, then again, no penalty. But if the node types are different, then there is a chance, then it penalizes that so that the annealer can be guided into converging into a better solution. And lastly, we build the matrix to use on Qdo solvers. Not lastly, but next, I'd like to talk about how we designed the experiment. So we made our own data set of code fragments, and from these 6 original code fragments, we manipulated them to make their type 2 and type 3 code clones. So essentially, somewhere we changed the variable names or the identifier names, or somewhere we added or removed or reordered statements to make them into type 3 clones, and so forth. So essentially, we have 25 original different code fragments that we know the ground truth of. We made our own data set because we wanted to be in complete control of the structure of the ASTs, so that we knew the ground truth when we tried to compare them with the results we got from the quantum annealer. So essentially, we had 25 code fragments, and each of those code fragments were compared with every other code fragment, which means that the AST of every code fragment was attempted to be mapped onto the AST of every other code fragment, giving us 325 pairwise comparisons. And we did this for two types of DQM formulations. One was with the node type constraints, where we were penalizing nodes of different types being mapped onto each other. And the other was without node type constraints, which means that we were only comparing and mapping the topologies. So we did those experiments 10 times each, which gives us 6,500 total queries to the quantum computer access through DWave. And here we have the energies, normalized average minimum energies without node type constraints. So every number here is essentially the resultant minimum energy we got from solving the QDO on the quantum annealer, and divided that by the number of nodes in the smaller graph of any two given code fragments. So essentially, this is a measure of the similarity of the two code fragments. We designed the QDO model in such a way that if there is a perfect mapping from one AST to the other, it would minimize to the lowest possible energy state. So essentially what we have here is the lower the energy, the more similar the two code fragments are. And by contrast, the higher the energy, the more dissimilar the two code fragments are, because the node mapping penalty and the edge mapping penalty has increased the energy of that QDO model for that particular instance. So if you see here along the diagonal, you see that most values are 0 or 0.0, which means that the code fragments that are being compared to themselves are mapped perfectly onto each other, which is expected. And as you can see in the blocks here, the code fragments that are similar, like type 2 code clones of type 1 of original ones, are also very close to 0 or 0 because they are also very similar. The dissimilarities increase as the types of codes become very different. Like for type 3 clones, the energies are higher. And if they're very dissimilar, then the energies could be as high as 0.64. But so this is how we know that the QDO model does detect code clones. But can we do better? Can we have a higher contrast in the resultant energies that we got, so that it is easier to distinguish between type 1, type 2, and type 3 code clones using this formulation? And the answer is the node type constraints. You will see in the next results here that there is a stark contrast in the results we got. And here, unlike the previous one where there were some values that were higher than 0, here all the values are 0 when along the diagonal are 0. This means that this converges to global minima better than the previous formulation because of the addition of the node type constraints. What's more is that this formulation results in higher contrasts in the resultant energies, which means that it is easier to have a threshold of seeing where do we find type 3 code clones, because we knew the ground truth from the custom data set that we made. And I also did a time performance and scalability study for this. And I realized that, and on the x-axis, we have the solution, time to solution in milliseconds. And on the y-axis, we have the size of the problem, which is the number of nodes in one graph of one code fragment multiplied by the number of nodes in the other graph of the other code fragment. So time seems to be somewhat unrelated and relatively independent of the complexity or size of the problem, and seems to be peaking at 135 milliseconds here. So finally, the key takeaways of my research are that I was able to detect type 3 clones successfully, which is computationally difficult to detect. There is a 75% increase in time to solution for 2000% more complex code, which means that the least complex code, two code fragments, uh, are 2000% less complex than the most complex two code fragments. This is not a comment on the quantum. This is not quantum speed up because there is no algorithmic or computational speed up here. It is just a technical limitation that we faced. And lastly, we can also see a 3 times higher contrast in the energy levels when using node type constraints, which proves that the node type constraints were essential in making this a better formulation. So finally, I'd like to conclude and talk a little bit about why this research is significant, is that this is probably the first formulation of code clone detection as an optimization problem of subgraph isomorphism. It's probably the first formulation of code clone detection as a QDO, and also probably the first implementation of code clone detection in a quantum annealer. And another contribution that we know worked is also the formulation of subgraph isomorphism problem using node type constraints. So essentially, you can compare two given graphs uh, and see if they're subgraph isomorphs or if each other or no, or if the smaller graph fits onto the larger graph or no. And you can do it better using this formulation because it compares the node types information of the two graphs being mapped. And lastly, it is a successful experimental verification of type 3 code clone detection using a quantum computer. Thank you.
Thank you for your talk. So let me quickly ask if you can tell us why do you call them QDOs and what's AST?
Sure. QDOs are QBOs, which are quadratic unconstrained binary optimization. But we chose to use QDOs, which are quadratic unconstrained discrete optimization models, because we wanted the results not as 0 or 1, but we wanted the result as the node names. So essentially, we wanted the results to um, have the names of the nodes being mapped onto other nodes. So that's why we used a QDO instead of a QBO. And an AST is an abstract syntax tree, which is essentially a intermediate representation of a given code fragment. And this is what happens when you compile any given piece of code. It gets converted into an AST, which is an intermediate representation, and it holds the semantic information of a piece of code. And that is what is used by the compiler to understand what's actually happening in this text here.
So you're saying that the nodes are variables and the links are what? Or something else entirely?
No. So the nodes of one graph are discrete variables, and the nodes of the other graph are the cases of those variables. So how the DQM formulation, discrete quadratic model formulation works in DWave is that you have these discrete variables, and they can be mapped to different cases in some like discrete cases like 1, 2, 3, 4, or Paris, Rome, LA, San Francisco instead of just 0 or 1. So essentially, the QDO model builds on top of the QBO model by having one hot encoding of the binary variables.
I see. Yeah, okay. I understand that. I was just kind of not entirely sure what AST, how is AST constructed, but I guess I can look it up. Yeah, thank you for your time, and yeah, let's meet again next week.
Sure.
Um,
Thank you.
Great.